So the last conic section we're going to take a look at are hyperbolas, the set of all points where the absolute value of the difference between two fixed points is constant. So how that looks, and just like with ellipses, we have major and minor axes. It could be oriented in two different ways. So first, the horizontal hyperbola. So here's x and y axis. The hyperbola looks something like this. Think of it as two mirror-imaged parabolas. Is basically what it is. Not exactly, but you can kind of think of it like that. The two hyperbola, it's one hyperbola, it's not two, it's one hyperbola. They have some similar things that we saw in ellipses and other things. There is a center to this. The center of the hyperbola is not actually on the hyperbola. It's not even in the hyperbola. It's in between the two parabolas. We would call that the center, call that C. The two fixed points are called foci, just as they were before. Those would exist here, say, and here. I'm just eyeballing them. So that would be focus 1, and that would be focus 2. The spot where the hyperbola, how do I want to say? It is exactly like it is with a parabola. It is the vertex. We have two vertices. The vertices are here and here. Two different vertices. Okay, so just like with an ellipse, we had vertices, we had foci, we had a center. We have the same thing here. Imagine if these go on forever, but imagine if they didn't. Imagine if the drawing that I have, the blues, ended, if we were to kind of take an ellipse, cut it, and then separate it in this fashion. That's kind of what we have. So those are some ways to think about it. So this is a horizontal hyperbola. A vertical hyperbola, just simply, like I said, take your computer, turn it on its side, and you'll see the vertical version of it. Don't actually do that. I don't want you breaking your computer. We have two different equations for the hyperbola. They're going to look very, very similar to the equations for an ellipse. Here are our equations for the hyperbola. All right, poof, like magic, there are the equations for horizontal and vertical. Notice it's just like with an ellipse. In fact, it looks almost identical to the ellipse equation. The only difference is that in a hyperbola, the sign between the two is a subtraction sign, not an addition sign. Otherwise, it's exactly the same. They equal 1. They have different numbers down the bottom. With an ellipse, A had to be bigger. Whatever came first had to be the bigger one. That told us whether we were horizontal or vertical. That's not the case here. A can be bigger or smaller than B. There isn't any stipulation as far as the size of A and B. We know it's got to come first because it's a subtraction here, and so if the coefficient in front of x at any point in time is positive, that's going to go first, right? Or not necessarily at any point in time, but when you get into the final answer. The coefficient in front of the parentheses on x should be positive, then it's a horizontal ellipse. If the coefficient in front of y is the one that's positive, then it'll be a vertical ellipse. So A and B could be any size at all. B has no meaning, whereas before B was half the distance with an ellipse, it was half the distance of the minor axis. In this case, I don't have a minor axis, and so we don't even have a major axis. And so A and B give us different pieces of information, but they're very similar. A is the distance from the center to the vertices. And we have two different ones, so you would add A and subtract A, either to the x value or the y value. How do you know? Is it horizontal or is it vertical? If it's horizontal, you will change the x, and if it's vertical, you'll change the y. B doesn't have any play in this, where B before, like I said, was the length of the minor axis. It doesn't have any play in this outside of helping us get C. C comes back again. C is the distance from the center to the foci, but now C squared is equal to, it is the Pythagorean theorem, A squared plus B squared. So if you recall with an ellipse, once again, with an ellipse, these two signs that I just highlighted are positive, and when we calculate C, it's A squared minus B squared. Now, with a hyperbola, the signs in between in our equation are negative, and to get C, it's A squared plus B squared. So it's just a complete opposite. Everything else is going to work the same. We're going to see a couple quick examples of how to write the hyperbolas and get the information we need, and we'll get those on the next slide. All right, so here we are with our example, right? The standard equation of the hyperbola. We know the foci are at -1, 2, and the vertices are at 0, 2, and 4, 2. -1, 2, and 5, 2, excuse me, for the foci. And the vertices are 0, 2, and 4, 2. So first we have to figure out if this is a horizontal or a vertical ellipse. It's easy. You simply look at what value is not changing, because only one can change unless it's a tilted hyperbola, tilted ellipse, tilted whatever. We aren't going to deal with those. We'll talk about those in a later video, but we're not going to deal with those. So this is either horizontal or vertical. Since the y values don't change, x values are changing. X is horizontal, and so this is a horizontal ellipse, which means it's going to have the form where x comes first. Let's go ahead and get that standard form up here again. And like magic, there it is. So we know this is how our equation's got to look. Our job is to figure out h, k, a, and b. Well, h and k are going to be where the center is. I don't have the center, but I have the foci. Just like it was with an ellipse, the center is going to be in the middle of the foci. Not only that, but the center of the ellipse is also going to be in the middle of the vertices. So I can find the midpoint of either one. To find that midpoint, regardless of which pair I use, if I use the foci, then the midpoint, obviously the y value is just going to be 2. 2 plus 2 is 4, divided by 2 is 2. If I use the foci, -1 plus 5 is 4, and 4 divided by 2 is 2. If I choose to use the vertices, again, the y values, 2 plus 2 is 4, divided by 2 is 2. The x values, 0 plus 4 is 4, divided by 2 is 2. So hopefully we can clearly see that this center is the midpoint of both the foci as well as the vertices. That center is going to allow me to find h and k, no problem there. And so now I need to figure out what is a and what is b. So if you recall from the last slide, let's pop back there again. A is the distance from the center to the vertices. So I can figure out A, knowing that it's the distance from the center to the vertices. I can cruise over to this problem. I see my center is at 2, 2. My vertices are at 0, 2, and 4, 2. So if I look at the distance from the center to the vertices, again, you could do distance formula, but you don't need to. The y values are the same, so it's just how far apart are the x values from 0, 2 to 2, 2, or from 4, 2 to 2, 2. That's a distance of 2. So A is going to equal 2 because that's how far away the center is from the vertices. If we jump back to the last slide, we also see something about C, that C is the distance from the center to the foci. Okay, no problem. So I can figure out what C is from my center to my foci from 2, 2 to -1, 2, or from 2, 2 to 5, 2. Either way, the 2's don't matter, the y values don't matter. We can just count the x values. C is going to be 3. So now that I have A and I have C, I can easily figure out B using my formula of C squared equals A squared plus B squared. If we were actually in class, we would take time and investigate that, and I would show you how that actually works. But I don't have the time in these videos, and we're not going to worry about it. Just lock that information in. And so if we plug in C is 3 squared and plug in A is 2 squared plus B squared, if we work that out, we will clearly see that B ends up equaling the square root of 5. So now I have all the pieces of information that I need to write the standard equation of this ellipse. All I need to do is plug in all that information. I know from my blue equation that it's going to start with x minus h. H is 2 because h is the x value for the center. So x minus 2 squared over a, not necessarily the biggest, just whatever a is 2, but it's a squared, so 2 squared is going to put us a 4 there. Minus, now we do the y. Y minus k. K is also 2 because the center of this hyperbola is at 2, 2. So y minus 2 squared. All of that will be over b squared. B is the square root of 5. If I do the square root of 5 squared, it is 5, and that equals 1. Always equaling 1. There's the equation of our hyperbola that has the information that was given to us, foci at -1, 2, 5, 2, and vertices at 0, 2, and 4, 2. Notice that A is 4, B is 5, A squared is 4, and B squared is 5, and so B is bigger than A, and that's okay. I know it has to go in this fashion because it's a horizontal hyperbola, and I know it's a horizontal hyperbola because it's the x values that are changing. That's what you got to look for when you're given foci and vertices and things like that. If the x values are changing, it's horizontal, but if our y values were to be the ones that were changing, then it would be vertical. So there's our first example. On the next video, which will be our last video on conic sections, we're going to take a look at one more hyperbola example, completing the square one more time, and then we're going to look at how to determine whether we have a circle, an ellipse, a parabola, or an hyperbola based on a general equation. So that's coming in the next video along with some homework. So look for that. Until next time, have a wonderful day, stay safe, and stay healthy.